In this video, I will be talking about what is a sequence and how to find its limit, if we can. A sequence is just a list of numbers. It doesn't even have to be numbers, but since we're in math class, we kind of care about the numbers. Here we have three sequences, nothing to write home about. 1, 1, 2, 3, 1, 1/2, 1, 4, 3, 3, 5. That one's kind of a funky one. If you can figure out where that comes from, I'd like to see that. So here are just three average Joe sequences. The formal definition of a sequence is just a function from the natural numbers to the reals. We say the natural numbers because we'll say the first one is this, the second one is this, and the third one is this. If you want, there's a web page listed below that has a list of integer sequences, which is really odd since there are uncountably many sequences and they can only list finitely many. Anyway, it's kind of fun to play around with sometimes. The notation we use for sequences varies. We can list the elements. We could say a sub n where we know what a sub n is, or a sub n is defined somewhere else. We could try to be specific and say a sub n where n goes from 1 to infinity, or we can actually put the definition inside the curly braces and say n going from 1 to infinity. Let's look at a couple sequences that you should already know and love, of course, because sequences are way cool. The arithmetic sequence is of the form a plus b, a plus 2b, a plus 3b, etc. Typically it's denoted by a plus n times b. So you're adding b to each of the previous terms. For example, let's look at this one. We have 2, 3, 8, 11, 14. So I start with 2 and I add 3, then I add 3, then I add 3, then I add 3, etc. Keeps going on and on forever. Another sequence you've probably seen, hopefully, is a geometric sequence. Same idea as arithmetic, except instead of adding for each term, you multiply. So we've got AR, AR squared, AR cubed. Usually it's denoted by a sub n is equal to a times r to the n. Let's look at an example. Here we have 2, 4, 8, 16, 32. So I started with 2 again. I multiply by 2, multiply by 2, multiply by 2, multiply by 2. Finally, let's look at the Fibonacci sequence. I know you've heard of this. Everybody makes a big deal about the Fibonacci sequence. The Fibonacci sequence is typically thought of as this one, though there are lots of Fibonacci sequence. Depends on what your first two terms are. But this is the standard one we all see, with the golden ratio and all that shit. You start with 1, 1. To get the next one, you add the two ones to get a 2. And then you add the next two. The next ones is a 1 and a 2. You add those two to get the 3. Then the next two is a 2 and a 3. You add those to get the 5. You add the 3 and the 5 to get the 8, etc. It's too messy to do any more than that. But you get the picture. To get a term, you add the previous two terms. Now, what can we say about the limits of these sequences? Well, one nice thing is if we know that the limit of a function is L and f of n equals a sub n, then the limit of that sequence is L. If L is a real number, we say a sub n converges to L. Otherwise, we say a sub n diverges. So this is nice. Now we can use all those rules and regulations and theorems that we learned about limits and bring them into figuring out the limits of sequences. For example, let's say we have a sub n equals 3n squared plus 2n minus 5 over 5n squared plus 1. A sub 0 is -5. A sub 2 is, I don't want to calculate. So the degree of the top is 2 and the degree of the bottom is 2. Since the degrees are the same, as n goes to infinity, the limit's going to be the leading coefficients. Check this one out. Under the square root, I have 3 to the 4th plus some crap, and on the bottom I have n minus 1. Well, 3 to the 4th under the radical means I really have second degree on top and first degree on the bottom. Therefore, since the degree of the top is 2 and the degree of bottom is 1, this has to diverge because it's top heavy. The top goes faster. Lastly, a sub n is n cubed over 2 to the n. Now, we should know from limits that the top is a polynomial, the bottom is exponential, so it goes way faster than the top. Since it's bottom heavy, or the bottom goes faster, this has to be a limit of 0. Now we've got a grocery list of theorems. Sorry, has to be done. You have to make sure you are aware of these. They probably do these subconsciously, but let's just cover them and get them over with. If you have c times your sequence, you can suck the c out. As long as it has nothing to do with n, you can factor out the c. If you are adding two sequences and you want the limit of the sum of two sequences, then you can find the limit of the two sequences separately and add or subtract them depending on what you stuck in between them. You can also do this with multiplication and division as long as the bottom doesn't go to 0. Also, if you're taking the limit of a function of something and you know what the inside is going to, then you can f whatever the limit is. So for example, if I have n going to infinity of a sub n to the p, and I know what a sub n goes to, I can find that and then just raise it to the p. Let's look at an example. So let's say we have the limit as n goes to infinity of n plus 1 over n plus 2. Looking at that, I've got a polynomial over a polynomial. Both have the same degree, 1. So I'm looking at the leading coefficients. That means the inside goes to 1. And the natural log of 1 is 0. So the limit of this sequence is 0. We can also use L'Hopital's rule. Well, if you haven't seen it, it's used when you have a rational function, so crap over crap. And if the top goes to 0 and the bottom goes to 0, or if they both, top and bottom both go to infinity, you can use L'Hopital's rule, which is take the derivative of the top and the derivative of the bottom and take the limit of that new quotient. Typically, if we have a rational function, we can look at it and go, yeah, it's top heavy, yeah, it's bottom heavy. We know it's going to 0 infinity. But the place where it really helps us is when we have some weird ass shit like this. A sub n equals 1 plus 1 over n to the n. If I try to quote unquote plug in, I'm getting 1 to the infinity. 1 to the infinity is an indeterminate form, so we need to do some jiggling. The typical jiggle we do with this is, because we know e to the natural log of crap is just crap, because the e and the natural log cancel each other out, we pull that trick. And if I've got the natural log of 1 plus 1 over n to the n can come out front because of our laws of logarithms. So I have 1 plus 1 over n to the n. I can rewrite that as e to the n natural log of 1 plus 1 over n. Now, e ain't going anywhere, so all I need to do is figure out where this exponent goes. So let's do that. I have limit as n goes to infinity of n times natural log of 1 plus 1 over n. If I try to plug in, I'm going to get infinity times 0, also the indeterminate form. And if you tell me that's 0, I'm going to smack you. 0 times infinity is indeterminate. So I need to shove something to the bottom, either the n or the natural log of stuff. N is the easiest one to push to the bottom, so let's do that. So now I've got the limit as n goes to infinity of the natural log of 1 plus 1 over n all over 1 over n. The top is going to 0, the bottom goes to 0. Sweet! We can use L'Hopital's rule. Think. Typically when I do L'Hopital, I'll put a little asterisk here, but I thought for people who may not have seen it, I'll go ahead and spell it out L'Hopital. So the derivative of natural log of crap is 1 over crap d crap. So 1 over 1 plus 1 over n. The derivative of 1 plus 1 over n is negative 1 over n squared. Again, derivative of 1 over n is negative 1 over n squared. So this is nice. Those guys cancel. I only have to look at the leftovers, 1 over 1 plus 1 over n. 1 over infinity is 0, so the limit is 1. My original question was, I've got e to all that stuff, not just stuff. So the limit of stuff is 1. So my final answer is e to the 1 or e. Another way to determine what the limit of a sequence is to squeeze it between two other limits. So let's say I've got this L, and I've got this top sequence that is converging down to L, and I've got this other sequence that's converging up to L. And I have this green one that's bouncing in between the two, but always staying in between the two. Well, then the limit of the green dot sequence is also L. Not very mathematical. Let me give you a more mathematical definition. If there exists n naught such that a sub n is less than or equal to b sub n is less than or equal to c sub n for all n greater than n sub naught, and the limit of a sub n and the limit of c sub n both equal L, then the limit of b sub n must also equal L. Okay, what's this bullshit at the beginning? Okay, so it says there exists an n naught such that at every point after n naught, this inequality holds. Which means if there's some crap going on at the beginning, I don't really care about that. As long as at some point in the future being further along the x-axis, at some point further down the axis, as long as this inequality holds for all points after that, I don't care about what crap happens in the beginning. That's just noise. I'm worried about what's happening after that point. And if after that point, I've got b sub n stuck between a sub n and c sub n, and both a and c sequences go to L, then b sub n is squished in the middle, also going to L. Let's look at an example. Limit as n goes to infinity of sine n over n. Now looking at that, I can see that this is going to be 0 because sine of n goes nowhere. It just flops around like a fish. 1, negative 1, 1, negative 1. Whereas n is going to infinity, a constant over infinity is 0. But let's prove it using the squeeze theorem. Sine of n is between 1 and negative 1, so sine n over n is between negative 1 over n and 1 over n. Now as n goes to infinity, I know that negative 1 over n goes to a 0, and I know 1 over n goes to 0, which means my middle also must go to 0. So my limit is 0. Let's try one a little bit grosser. Now, n factorial and n to the n, we don't use these as functions because n factorial doesn't make sense unless n is an integer, positive integer. N to the n gets really snarky in places. So this only works if you've got integers anyway. But I want to try to squeeze this. Get it between two things that I know will go somewhere. Well, the terms are always positive. That's nice. So let's try to get a handle on this n factorial. Let's look at 3 factorial. 3 factorial is 3 times 2 times 1. I don't really care about the 1 because this is the 1. 3 times 2 is going to be less than 3 times 3 because you just replace the 2 with the 3. You're getting bigger, so the whole thing is bigger. This is equal to 3 squared. Let's try it with 4. 4, 3, 2. I'm going to replace this with 4, 4. Again, clearly bigger. 4, 4, 4. And there's 3 of them. It's 4 cubed. So in general, n factorial will be less than or equal to n to the n minus 1. Okay, now we can do some algebra. I know that n factorial over n to the n must be less than or equal to n to the n minus 1 over n to the n. Well, the power on the top is n minus 1, and the power on the bottom is n. So I've got an extra 1 on the bottom. This is 1 over n. Yay! We can do this, because I know 0 goes to 0. 1 over n goes to 0, which means the stuff in the middle must also go to 0. Let's look at some definitions relating to sequences. A sequence is increasing if a sub n is less than a sub n plus 1. Not less than or equal to, must be strictly less than. So it's always getting a little bit bigger as you go along. Similarly, a sequence is decreasing if a sub n is greater than a sub n plus 1. So it keeps getting smaller and smaller and smaller and smaller. If it's increasing or decreasing, we say it's monotonic, just so we can say things that are true for both of them, but we don't want to have to say increasing or decreasing, because that's a pain in the ass when you just say monotonic. Another definition we want to talk about is bounded. A sequence is bounded above if there's a number that none of the terms go above. A sequence is bounded below if there's a number that nothing goes below. Kind of makes sense. If it's bounded above and below, we just say it's bounded. Now, a neat theorem that we can use is if I know it's bounded above and it's increasing, well then it's got to converge because it's got nowhere to go. It's going to get closer and closer to that top part. Similarly, if it's bounded below and it's decreasing, it'll have to converge because it's got nowhere to go. A more generic way of saying this is a bounded monotonic sequence must converge. This is actually a little bit too specific. I can just say if it's bounded above and increasing, it will converge. Or if it's bounded below and decreasing, it will converge. So like this little guy trying to go up the stairs, he keeps climbing the stairs, he's going to get squished into the floor because he's bounded above. So we'll be working with sequences. We want to figure out if they are convergent or divergent, and if they're convergent, what do they converge to? To do this, we will need to remember our theorems from previous semesters about convergence and limits and L'Hopital's rule and which goes faster and all that good stuff.